Okay, let me introduce our speaker. Today we have Jen-Hsun Huang. Jen-Hsun is the CEO, co-founder, president of NVIDIA. How many people play video games? Just a few of you, okay. So you can thank Jen-Hsun for the technology that you get to use. And we're really proud of Jen-Hsun. He graduated from Oregon State in 1984. We just went up and looked at his picture again. And also with Jen-Hsun, we have his wife, Lori. Lori also graduated in our electrical engineering program. Her picture is up in 1985, if you want to go look at it. We were admiring the hairstyles. And, but we're really fortunate to have Jen-Hsun here today. He graduated, like I said, in 1984. He married his lab partner, Lori, in 1985. And then he got to work. In 1993, he co-founded NVIDIA, and the rest is history. So now it's been 20 years later, and the company is hugely successful to the point where they're expanding, and they're going to significantly increase their campus for NVIDIA. So they just are growing and growing and doing very, very successful. And they've moved from the hardware that you're used to for video games into the mobile space and tablets. If you have a Surface RT, that would have NVIDIA hardware. So with that, I'd like to welcome Jen-Hsun Huang and have him share his life experiences.
Thank you, Terry. Would you guys mind if I sat down too? That'd be all right, right? We'll just be among friends. I came here 30 years ago. And it's kind of amazing to say 30 years. I doubt that any of you are 30 years old. Lori and I were lab partners, and we were in a class of, I think she said about 80 students, and there were 3 girls. And so, as you could imagine, the odds are well, look out there, okay? The odds are heavily stacked against you. And so imagine the achievement to have scored one of the 3 girls, and it was unquestionably the most attractive. She was, so I had the best of a very small pool, and like Terry said, everything else is history. And in no small way am I saying that serendipity matters a lot in success. The fact that Lori and I were assigned to essentially the same group for I think it was electromagnetics, right? Was it fundies? Okay, it was E-fundies. And so we met serendipitously. But she surely wouldn't have been nearly as attracted to me if not for the quality of my work, and I think that's, and I don't mean that in any small way. Okay, I mean, big brains are attractive, and so for all of you big brains out there, there's hope for you. So 30 years ago, we were here 30 years ago, and the school has changed a lot. We were walking up with Sandy earlier today, and we noticed that it really shrunk. It seemed like a much larger university at the time, but the buildings are getting smaller and smaller. All the people are getting smaller. It just it's kind of one of those weird things in life where everything just seems smaller when you look at it again over time. I was 16 when I came here, and I think I was 20 when I graduated. And then I went off to work for a company called AMD. AMD makes microprocessors, and I fell in love with AMD because they had a poster in the lab that I was in. And the poster was the world's first bipolar microprocessor. It was made out of ECL, if any of you are familiar with that technology. Basically current steering. And using current steering, you're able to make gates. using ECL technology, they were able to build rather fast microprocessors. The chip that I worked on, I think it was 10 watts or something like that, and it was like 1 megahertz, and so you could almost see it coming. It was that slow, and so I fell in love with the idea of building microprocessors and building computers, and so I went to work at AMD, and I worked there for a couple of years, and my office mate left to join a startup called LSI Logic, and LSI Logic was and I was delighted to work at AMD. I enjoyed my job, and one day my office mate calls me from LSI Logic, and she said, this place is amazing, and they would really love to spend some time talking to you. And it turned out that when I was still here on campus, do we still do recruiting days, where companies come in and you go from booth to booth to booth, and so we did recruiting days, and LSI Logic was one of the companies that was on campus here at here on Oregon State, and they wanted me to go work there, but I decided to go to work at AMD. And then when my office mate went to LSI Logic, and when she got there, she said, my office mate, this guy named Jen-Hsun, and they go, hey, we tried to recruit him when he was back in school, and LSI was still a pretty small company at the time, and so they reached out to me again, and this time I realized what they were doing, because the first time that I talked to them, I really didn't get why it is that company and the work that they were doing was going to be important. And basically the work that they were doing was creating the idea of using design tools to create chips, and making it possible for system designers, when you think at the system level, to create custom chips that embody your ideas and systems. And I didn't really get it at the time when I was in school, because I was so obsessed about the idea of building something, not how to build it. And then after I went to AMD and I worked on designing microprocessors for a couple of years, I realized the real challenge isn't what you're trying to build. The real challenge is how you went about building it. And that design tools made us more productive. And LSI Logic was trying to pioneer that work, using design tools to make designing chips easier, and putting it in the hands of more people. And so 2 years later, after I've worked at AMD for a couple of years and realized how challenging it was to work at the polygon level and trying to design a chip that way, the idea of design tools really connected with me. So I went to LSI Logic, and the company was rather small. It was like 300 employees or something like that, and it had just gone public. It was $100 million. I don't even think it was a $100 million company at the time. It was a little tiny company, and there I discovered how powerful it was to use design tools to design chips. Years later, we invented the idea of high-level design, logic synthesis, logic optimization, static timing analyzers. These are all things that you guys probably use every day now. We used automatic test generation, test insertion, the idea of synchronous design, and not just thinking about what you want to build. That was important. Thinking about what you want to build is important, but what's even more important is to build it in such a way that tools can help you. This idea that a design engineer would build something, design something in a rigorous set of rules, so that the design tools could understand what you're trying to design, and therefore synthesize and help you optimize that design as a result. Created this whole word called design methodology. Okay, this is now a story that is 25 years old. At that time, the idea of the word design methodology simply meant to a designer, so you're going to constrain how I design, you're going to constrain what I design, And so the tool's not flexible, and therefore I'm not going to like it. Today, design methodology is no different in chip design than it is in programming. Design style, programming style, design methodology, programming methodology. That rigorous methodology that makes it possible for us to allow tools to help us was a psychology that we instilled in the industry starting in the mid '80s. I would say that simple little idea really changed how I saw the world, and how Silicon Valley was really changed. In fact, that the design tools that I was talking about was discovered by a young German, and this young German had just came to the United States, and he was a Stanford University student, and he had started a company under the acronyms Stanford University Network, and he was trying to design the next generation computers, and instead of using off-the-shelf microprocessors from Motorola, he thought that maybe he could design his own computer completely from scratch, because if he could do that, he could make this computer very small, and his vision was that it would be 8.5 by 11 motherboard, which was tiny at the time, and that he would design something that would be as powerful as 10 MIPS and have a display that had one megapixel, and have a network capacity of 10 megabits per second, and so that was his dream, and he heard about the work that we were doing at LSI Logic and reached out to us one day, and I spent the next some 2-3 years on the campus of another small company called Sun Microsystems. Are you guys familiar with this company? And the kid that I was working with, he's not a kid anymore. He was the first investor in a small other company many years later, which turned into Google. His name is Andy Bechtolsheim. Andy Bechtolsheim is probably the most important modern computer architect, and I met him in the mid '80s and the late '80s, and we worked on the SPARC 1 together. If it not because of the expertise I had developed in using design tools to design microprocessors and design computers, my relationship with him wouldn't have been started. He was looking for someone who could help him realize his imagination in computers, and design custom chips from it. Well, what I described today, this idea that you have some unique idea, whether it's a new computer or a new networking chip or a new storage architecture or a modem or whatever it is, whatever idea that you have that needs to be somehow realized in silicon, the path that goes from the idea to the silicon is all design tools, all design methodology, and it's all the stuff that we invented. And it was all done in the mid '80s. And notice I found that almost completely serendipitously. If it wasn't because of realizing that design methodology was going to be more important than what you designed, realizing that the design tools was going to be more important than what you designed. If I hadn't realized that and fell in love with it and became an expert in that area, the rest of my experience wouldn't have been possible. And so in the late 80s and the early 90s, while building the SPARC stations, and by this point I've worked on many generations of computers now, and my love for computers and computer architecture had continued to grow. A couple of really fantastic engineers reached out to me because they wanted a partner to help them build something that had never been built before. Those two engineers, Chris Malachowski and Curtis Preem, eventually turned out to have been the two friends that I started NVIDIA with. And our idea was very simple. Our idea about NVIDIA was rather simple. It was that gosh, there's movies, there's video, there's print, there's music. These are all mediums for expressing ideas. These are all mediums for telling stories. And we thought this incredibly complicated technology called 3D graphics that was used for workstations and military simulators, and they were massive in scale, and then required enormous amount of computation to synthesize in real time 3D graphics. That this technology might someday be so pervasive, if we could make it affordable, that it could be a new medium for telling stories. That this medium is powerful in ways that the other mediums can't possibly match. And the reason for that is because 3D graphics, as you know, is not pre-recorded. It's not pre-recorded. That every single time you use it, every single time you enjoy it, it's completely different. This is the only medium where you could be networked. We could share the world together, because we're synthesizing it, obviously, for every viewer. And it's interactive, it's shareable. It is, on the other hand, very, very complex. And so we asked ourselves, is this something that we could imagine people loving? Is this something that is worthwhile to tackle? Is this something that is really hard to do, so that we can continue to do it for some time to come? Okay, now we asked ourselves some really basic questions, and we were young at the time, and they were questions that I think are, and whether we asked it because we were wise, we asked it because they were smart. They're the same three questions I ask all the time today. I ask those questions all the time today. We ask ourselves, is this work something that we would really, really love to do? Is this work that is worthwhile to do if we were to be successful, and if it's hard to do? If it's hard to do. And the reason why we ask ourselves whether it's hard to do, the first two questions are relatively obvious. You shouldn't do anything that you don't love. You shouldn't work on anything that not with your casual time, with your life. You should work on things with your life that matters. The reason why it has to be hard to do is because fundamentally, if you start with the idea that you're surrounded by really extraordinary people, and this morning I met a young professor. His name is Patrick, and Patrick happened to have worked with my chief scientist, Bill Dally. And Bill Dally, if any of you know him, is one of the world's greatest thinkers in the area of parallel computing. If he's on your team, if Chris Malachowski's on your team, if Curtis Preem's on your team, if Jonah's on your team, if your teammates are the world's best at what they do, you better make sure that the work that you do is worthy of their life. And if you don't do work that is hard to do, that's worthy of their life, then it makes no sense for them to be on your team. And if they're not on your team, then you can't do great things. It's one of those challenging circles that that somehow we realized early on that we've always believed in, and we've always very carefully protected, that we do important work that is hard to do. And so 1993, I guess 20 years ago, this month is NVIDIA's 20th anniversary. 20 years ago, we asked ourselves those three questions about 3D graphics, and we came to the conclusion that 3D graphics was going to be really, really hard to get right for a very long time. And so let's test it. Well, first of all, one way to test it is that none of you have seen a video game where the imagery exceeds your expectations. None of you have seen that. In most cases, you look at it and you go, wow, this is really beautiful. Battlefield 3 comes out and you go, this is really wonderful. This looks fantastic. Okay, looks way better than Call of Duty. I'm not trying to take sides here, but you can see that I still enjoy the imagery we create. And so on the one hand, it's beautiful, but on the other hand, you could just imagine so much more. You could just imagine so much more. That the shadows aren't quite cast it right. It's a little bit too crisp. And oh boy, if the shadows were softer, if the dynamic range of the lighting was greater, if the geometry was more tessellated, and wasn't so faceted. If the world was more dynamic, you could imagine so many more things. If the textures weren't so blurry and so heavily filtered, and so if you could imagine so much more on the one hand, on the other hand, it's beautiful every time you see it. And so we think that that 3D graphics has got a long ways to go. Computationally, the idea that every single pixel is backed up with millions and millions of operations, and if you just multiply by the number of pixels, you could imagine how much computation we have to do over time. And so as a result, we felt that it was going to be sustainable. Now, if you test it another way, which is in the world of semiconductors, almost everything gets integrated over time. And it gets integrated, and you're fighting against Moore's law, if you will. And when you get integrated, you become software. So for example, there was an audio chip industry. There isn't an audio chip industry anymore. There was a video chip industry. There's no video chip industry anymore. There was a networking chip industry for computers. There's no real networking chip industry anymore. And storage and so on and so forth. And the reason for that is because it gets good enough, and Moore's law exceeds the capabilities that is necessary or is limited by other things in the medium, and as a result, you integrate it. But 3D graphics continues to be very, very the industry continues to be robust, and there are always things to do. And so we observe these things properly, that 3D graphics has an opportunity to not just be a feature of the computer, but it can actually be an industry all by itself. That there's a new type of processor that could come out from this called a GPU. So we invented the GPU, and we took it on a journey that's actually quite interesting that I'll tell you about. And so this is 1993. We had 3 employees at the time. We have about 9,000 employees today, and we have a site here in Oregon that we're very proud of. The GPU was interesting in a couple of different ways, and this is now. Let me tell you a story about the importance of knowing what you're doing and why you're doing it, and how that could change the outcome of your company, how that could change the outcome. So let me first paint the picture. The first thing I've told you so far is that what you build and how you build it are related things, but having a passion for how you build something could change how you see the world. Now, the second thing I want to tell you is the purpose of your work. In 1993, we were the first company to attempt to make 3D graphics consumerized. This was 1 year or 2 years before the PlayStation 2 was announced. Okay, you guys know the PlayStation 2, right? Okay, all right. The PlayStation 2, by my calculus, is probably the most important consumer 3D machine. It made 3D graphics more pervasive than just about any endeavor, even before we were successful in doing so. But in 1993, 2 years before that happened, we were the first company started to try to attempt to do that for general purpose computing for PCs. And 2 years later, there were 90 companies. And we started earlier at a time when DRAM was, and just remember what I'm about to say here, DRAM, 1 megabyte of DRAM, 1 megabyte, not 1 gigabyte, 1 megabyte. 1 megabyte of DRAM was $50. Okay, $50. And in order to have any convincing 3D graphics at a resolution of 640 by 480 VGA resolution, with the color buffer, two of them, front buffer, back buffer, and the Z buffer, okay, and enough space to hold textures, we needed about 4 megabytes. 4 megabytes, basically just the DRAM alone was, well, $200. And then you have to build a chip to go manage the DRAM called the 3D graphics chip. And then you got to mark it up for your profit. And then your distributors have to mark it up for their profit. By the time that you got this graphics card that does 3D graphics, it was about $1,000. And that's hardly a consumer price point. And so we invented this technology that made it possible not to have a Z buffer and not to keep texture memory in our frame buffer, but keep it in system memory. And we virtualized all this stuff, invented all this technology. And then 2 years later, 90 other companies showed up, 89 other companies showed up. And on one day, DRAM price fell from $50 to $5. And it did so because DRAM pricing, I learned something about DRAMs, and the surrounding and the assumptions that you make in building your company, that the DRAM is not a technology-driven pricing thing. It is a supply and demand pricing thing. That's why they call it a commodity. It's a little bit like pork bellies and orange juice and those kind of things. If supply exceeds demand, then the price keeps coming down until the two meet. Well, somehow demand supply equation changed, and then all of a sudden the assumption, the fundamental assumption of our company, which is inventing this technology, we call it forward texturing. No Z buffer was used. We used curved surfaces. That entire assumption collapsed. When the assumption that you're making about your surroundings change in such a fundamental way, then everything about your company, in fact, changed. Now notice, we had built a company for the right, with some assumptions, right, that 3D graphics was going to be good, but the technology that we had invented was based on an assumption that no longer was true. And we went from being the world's first company to be working on something to becoming the world's last company to be doing it right. Because every other company that was out there was using a technology based on OpenGL, which is the technology we're using today, using triangles, using Z buffers, using inverse texturing instead of forward texturing, curved surfaces, and no Z buffers. And so it was a night in 1995, and we were sitting here. We're running out of money. We have an enormous number of competitors, and our technology at this point, with no exception whatsoever, the industry considers to be wrong. It's wrong because the programming model is so different than everybody else's, and all of the challenges of programming our architecture was unnecessary anymore because DRAMs were so inexpensive. And so in 1995, I still remember a very, very difficult night, and Chris Curtis and I were now talking about what should we do. You know, what should we do? We were the first, and when you're the first, and you invented all the stuff that alleviated this huge cost of DRAMs, you felt like you had an advantage, a reason to exist. You might win. All of a sudden, you're the last in the world, or you're the first to do it wrong, however you want to think about it. Now what do we do? Now what do we do? If we were to adopt the same techniques that everybody else adopted, we would be one of 90 people. They were better funded than we are at this point, and we're running out of time because when you're a startup, money is time, and you're running out of time. And what do you do? And it was rigorous. It was rigorous discussion, or that's uh, talking at each other at incredibly high volumes. Okay, and the question is, what should we do? And ultimately, I think the psychology or the sensibility that won the night is this. Maybe we don't know whether we can win if we did it the way everybody else did it, but doing it the wrong way certainly won't lead you to the right place. And so at this point, it is clear we're doing the wrong way, and nobody's going to support our architecture in the way that we define 3D graphics if it's unnecessary. So we decided that night to go home and say, look, we're going to stop doing it the way that we did it before. We're going to stop the fundamental technology that we invented our company to go do, that we still believe in the future of 3D graphics, that we still believed in each other. That was net how we went home. How we would continue to be successful, don't know. What strategy we would find to differentiate ourselves, don't know. And how we would get the rest of the money to build a chip the right way, inverse texturing and Z-buffered and triangle-based, don't know. But those are in the final analysis what I would consider details. You know, at this point, although it didn't seem like details at the time, it seems like details now to me. The two things that were quite fundamental that I continue to believe to be true, and would have been enough for me to have started the company altogether, was two things. One, do I believe in that work? Is this something that we would love to do? Is this something that we could be world-class at doing? Is this something that is hard enough to do that we could do for a long period of time? And the question about my teammates. Are these people that I want to go to battle with? Are these people that I want to stay up all night with? And do we believe in each other? Those two questions, if I got the right answers from, would have been more than plenty to start something new. And so we went home. We came back and the next day was where the rubber meets the road, and we said, okay, so one of the founders said, okay, all right, so now we decided that we're going to do this. What's our strategy? What's our strategy to win? How are we going to beat everybody else? We're the last company now. And you guys know this about if you play games, if you enjoy competing, if you enjoy any type of strategy-oriented activities, you know that it's oftentimes good to be first. It's oftentimes good to be last. The benefit of last is that you know what everybody else is doing. Okay, and then the next thing was you have to be very concerned about a company that has no future. And so the reason, let me explain that to you. You know that if you're playing a game to manage your resources, okay, you're playing a game to manage your resources. You could deploy certain types of strategies, and you can't deploy certain types of strategies. However, if you're playing a game and this is your last hand, and you know it, and you're playing it like this is your last hand, and you're not coming back, you're going to play it a little different. Do you know what I mean? When somebody goes all in, they can do things that you can't do because you're trying to manage your resources. It was 1995, and we had the presence of mind to observe these two facts. That we were, in fact, now the last. We can go and study what everybody else is doing first before we decide what to do. And then number two, we are all in. Don't play to come back. Don't play as if there's another hand. And if there is another hand, let that be a surprise, and then we'll go figure out what to do next. And so we literally took everything we had, and we built something that no one else in the world would build. So for example, we built the world's largest non-microprocessor chip ever built at the time. And the reason for that is because I wasn't worried about my cost. If you were running a business, you have costs, you have gross margins, you have financial results you have to manage, but I didn't. I built a chip that physically was as large as anyone could build at the time. Instead of doing all of these hacks in integer, we just did our entire pipeline in floating point. Why sit there and shift numbers around? Let's just do it all in floating point, and instead of doing creating a floating point setup engine that took 30 clocks to set up, we pipelined the living daylights out of this floating point engine and had enough units in there to set up a triangle every clock. Now, in the end, this chip was huge. It was massive. And when we went to try to build it, TSMC was a small company at the time, they said, you guys, this is nuts. This thing is going to cost way too much. I said, that's good. That's good. We just want to make sure that this is the most powerful chip the world's ever seen. If we're going to leave a mark, okay, if we're going to leave a mark, leave a huge hole. Right? Don't just leave a little tiny divot. Number one. Number two, the challenge with companies at the time was this, and 3D graphics was particularly challenging this way. You have to build a chip first, and then you can develop the software. And after you develop the software to run the chip, you discover there's a bug in the chip. You got to spin the chip, which then you build the chip, you get back, you do the software on top of it. The iteration loop caused the development cycle times to be about 2 years. From the moment you tape out a chip to the moment you get it to the market was about 2 years. Well, we didn't have 2 years. It's not complicated to do some simple math. We had 9 months. We had 9 months of money left. And so we decided that, well, if you have 9 months and it takes 2 years, obviously you don't have 9 months. And so what if I took some of the money and I invested in a machine that makes it possible to do our software development before we taped out the chip. And so at the point of tape out, the chip had to be deemed perfect, because it's the last tape out we're going to do. Okay, so we got our the company was much smaller than this room here, and it was umpteen people, and we got everybody together, and I said, hey guys, look, here's the dilemma. If we did it the old-fashioned way, it would take 24 months. We have 9 months of money, so we don't have 24 months, so we're not going to be able to do it the old-fashioned way. However, here's the problem why the old-fashioned way was necessary. But suppose we bought this machine from a company that is going out of business. I had heard about this machine. It's called the ICOS emulator. To emulate your chip in this big, huge machine that looks like a refrigerator. If we gave them 3 months of our life, so now all we had was 6 months left, we could buy their machine and keep them in business for an extra 3 months, and we could prototype our chip, do all the development on top of this emulator, pretend like it's our chip, run all the QA, run all the games, run all the VGA tests, run all the Microsoft tests, so that when I tape out that chip, I know, or I believe, I hope, that it's perfect. And that chip, I will start production on day 1, sight unseen. And so they said, you know, Jen-Hsun, you've really lost it. You've got, and I still remember these conversations. It's like, you know, 9 months, that extra 3 months, we might be able to find more money. I said, we're not going to find more money. It makes no sense to find more money. I believe in you, you believe in me, but nobody's going to believe in us. There are 90 other companies to go believe in. Why believe in us? We got to do it this way. So we decided that we were going to go and buy this emulator from a company that had no other customers. We have a law in our company: startups don't invest in startups. Okay, startups don't rely on startups, and that's a law because of what I experienced. It is as a Hail Mary of crazy levels, and so we bought this machine with $1 million, 1/3 of our life. We took 1/3 of our life, and we bought this $1 million machine. And because it was 1/3 of our life savings, we made it work. And we brought up Riva 128. Does anybody know Riva 128? Riva 128. Riva 128 is the world's first graphics chip that actually exceeded people's expectations of what graphics chips can do. And there's a lot of reasons why it was so complicated, but to have done that. But anyways, Riva 120 was very important for our company and also for the industry. But ICOS delivered their machine. They stayed around long enough to help us bring it up before they went out of business. And we brought up the entire Windows stack, VGA stack, all of our drivers. We ran it at one frame every 30 seconds, minute or so. We had our QA, we had one QA engineer, Andrew Martin. He still works there at NVIDIA today. And he sat in front of this emulator that ran one frame every 30 minutes or whatever it is. And he QA'd our entire chip that way. He ran every application. He never went to sleep. And on the day that we taped out the chip, I told the guys that we shouldn't tape out the chip if we don't know that it's perfect. If it's perfect, and you think it's perfect, and we've done everything we could to make sure that it's perfect, then we should go to production right away. Now, the good news is we had no money left. Okay, so the bad news is, why would any factory start manufacturing your chips if you had no money left? And so the answer, of course, is don't tell them. And so we had we started the production of Riva 128, and sight unseen we went to production because we're out of time. We had to catch up to the competition, and the chip came back, and fortunately, it basically worked. It basically worked. There were, if any of you in the audience understand 3D graphics, there's these different blend modes about how you manipulate the frame buffer, and Microsoft in DirectX specifies 32 blend modes at the time, and we were compatible with a whopping 8 of them. Okay, and so we explained to our customers that 8 is all you need. Okay, you'd be lucky if you used 6 of them. But what we really did do is we ran out to all of the developers in the world, all the game developers, and we said, please don't use the other 24. Please. If you want to make explosions, you want to make them transparent, could you do it this way? Use that mode. Don't use the other 24. If you use the other 24, we're cooked. We are cooked. Okay? You love a lot of things about Riva 128. Okay, so it doesn't have 24 blend modes. There's a lot of things to love. Okay? I mean, this kid is not perfect, but there's a lot of things to love. Okay? And so it turns out the rest of the industry fell in love with Riva 128 just like we did. We had to love it. It was our only child. And so we ramped up the production and then we went to town. Riva 128 became the world's first 100 megapixel fill rate texture map Z-buffered engine in the world. We made it possible for you to enjoy 640 by 480 graphics with many layers of depth complexity, completely alpha blended, with a CPU on the other side, which was just a 486, running at 100 megahertz, for us to offload enough of the setup, the triangle setup, that you could actually render 3D graphics at 30 hertz. It was the first time that had ever been achieved, and Riva 128 took off. The demand took off. The interesting observation, though, was this, that 3D graphics was a unique medium, that the technology necessary to make 3D graphics possible was extraordinary. It needed all the transistors we gave it and more. It needed all the transistors we gave it and more. The first Riva 128 was 3 million transistors. The latest generation we just announced, called GeForce GTX Titan, is the same processor that goes into our nation's fastest supercomputer, the Titan, and we decided to name GeForce after that supercomputer. Titan, GeForce GTX Titan, this GPU, internal code name was K110. K110 has 7 billion transistors. 7 billion transistors. And the only thing from 3 million to 7 billion, so 2,000 times in 20 years. Way, way, way faster than Moore's Law would have suggested. So as large as we made Riva 128, we didn't make it large enough, apparently. And we've been trying to make it larger ever since. And so now GK110 has 7 billion transistors and a few gigahertz and all these processors, 2,000 processors inside. I just wish I had 14 billion transistors, and so that's what we're off trying to do. How do we put more computation in here? The thing that now that I'll talk about is reinvention. So Riva 128 saved our company's life. We were the last graphics company to show up. We were the first to have started, and you can tell when people write you off. Okay, you can tell when people write you off. Every industry has analysts. On the year we were founded, that analyst spoke about us and about the vision. It was, oh, it's fantastic. These guys are going to change the world. 2 years later, there were 80 other companies, right? We weren't on that list. When you fall off the industry analyst list, before you're actually dead, first of all, number one, you think it's unfair. Okay? When other people write you off before it's actually over. And number two, you just know that somehow you're on the wrong track. But nonetheless, all of those other 80 companies are no longer in business. Somehow we made our strategy work. Then Intel came along, and 3D graphics was really important to Intel, and they wanted to integrate 3D graphics like they integrated video and audio and networking and storage and you name it, okay? And for all intents and purposes, it makes sense. It makes sense. And so the challenge for us was, how do we reinvent our company? And now let me explain to you the difference in how we saw the world and how everybody else saw the world and how it saved our lives. Well, I told you earlier that our mission statement was around the idea that 3D graphics was going to be a very important medium for telling stories. Now, when I say this, that 3D graphics is a medium for telling stories, it just sounds like foo-foo stuff. Because it is kind of foo-foo stuff. It's a little bit open-ended in the nature of that perspective. Other companies had things like this, their mission statement, and you read it in many of their companies' PowerPoint slides. Our mission is to build the world's fastest graphics chip. Our mission is, in the case of, at the time, the largest PC chipset company, at the time was a company called Cirrus Logic, a really fine company. Their mission statement was, we would like to be the one-stop shop of all industry standard PC compatible components, of which case graphics was one of them. Well, here's NVIDIA. We want to be a medium for telling stories. Okay? Well, let's see, what would happen? If your mission statement is to build the fastest Well, fastness is measured by something, is measured by today's benchmark. So your entire universe is captured in what are the existing definition of fast. And the existing definition of fast, the test that you're provided, the test that they provide to determine whether you're a good person or bad, good company or bad, is based on that one singular test. It's a little bit like the SAT test. Okay? The only difference is this particular test never changes. And so you're looking backwards in time. And if you could make that thing go fast, somebody else can make that thing go fast. And your entire horizon is limited to that test. Another mission statement would be, I want to be the one-stop shop for all industry standards. Okay, well, meeting an industry standard is obviously not very complicated. Once you meet it, everybody else meets it, by definition. How could you be, right? How could you differentiate among standards? So you're rather constrained. Your whole point is, I just want to be the one-stop shop. I just want to be the one-stop shop. Doesn't say anything about making it wonderful. It doesn't say anything about the future. It doesn't say anything about expanding horizons. It doesn't say anything about anything. It's just, I'm the one-stop shop. Well, it turns out that we never called it a mission statement. It was just our perspective. Our perspective is that 3D graphics is going to be this incredible medium for telling stories. Now, the problem is 3D graphics at the time, OpenGL, was rather constraining in its ability to tell stories. And so every triangle was rather rigid. The way you address textures was rigid. The blend modes are rigid. Okay, the pipeline is rigid. And we asked ourselves, well, what could we do to make this medium more expressive for telling stories, so that all the video games would look different instead of the same? Because at the time, if you remember, anybody know Quake? Is anybody familiar with Quake? Okay, so John was gosh, he was so young, and we were all so young, but he was even younger, and he came up with this game called Doom, and Carmack is just a fantastic programmer, and he wanted to move everything to real 3D, and so he created the world's first game, consumer application for OpenGL. If it wasn't because of Quake, OpenGL wouldn't have been nearly as important as OpenGL is today. He completely changed the world because of one game. Well, the problem with Quake, if you go back and look at it, every version of Quake looked exactly the same. That chalky texture looks exactly the same. And we say, look, if we don't make this medium more expressive, how can we tell stories that are more diverse? How could different artists express their art in a different way so that Carmack's game looks different than Sweeney's game? There's a style about it. There's a style to that art, and I could pick it out. Oh, that engine is from DICE. That's the way they do it. Oh, that engine is from Epic. That's the way they do it. It looks like their stuff. Well, the only way, of course, is to make it programmable. We invented this idea called programmable shaders. The day we invented it, there was no value in the technology, but I think history would suggest that programmable shaders completely changed 3D graphics today. It made it possible for everybody's game to look very different. Now, the beauty of it for us, how it saved our company, was the last generation of fixed function graphics acceleration was commoditized in about 5 years. If it wasn't because of programmable shading, we wouldn't have opened up a brand new horizon that made it possible for us to have this sustainable capability that consumed more transistors, that prevented the GPU from getting sucked into the CPU or the chipset. And so it extended the life of our company. And then one day we said, but we made graphics programmable, but there's so many algorithms that programming the shaders isn't enough. What if we wanted to bring dynamics to the world? What we wanted to make it possible for lens effects and post-image processing effects to really bring the content to life. We decided to go into this era called computational graphics, invented this technology called CUDA, which opened up the GPU for programmability for all kinds of things. Each one of those junctures we risked our lives doing. And in fact, you can go back to time, and all you have to do is just watch our stock price. Every time we invented something new, our earnings go to less, okay? Every time we invented something new, our earnings get less. And then all of a sudden, at some point, when the technology gets adopted, the earnings fly. And then a few years later, if they couldn't leave it alone, they invented something new, and the earnings crash again. That's what shareholders really hate about me. However, the question is, what's the definition of success? Good share price is important. In fact, it is very important. It is very important. But for many companies, it's harder to manage all three at the same time. And so the question is, are you doing work that's relevant? Are you doing work that is exquisite? Or are you doing work that results in a great stock price? I've not figured out how to do all three at one time. I've not figured out how to do all three at one time in a short period of time. Over the long term, all three do seem to work out. I mean, if you squint it and look at our company from very, very far away, we're creating shareholder value like no one's business. Okay. However, it's very, very volatile in between. And what we've always tried to tell ourselves is the most important thing is to do important work, to do relevant work. Then you have to do it with the best of your might. You have to be proud of your work. Irrespective of whether other people value your work or not, you have to be proud of your work. Just give you an example. We do all kinds of work inside the company that other people don't see. There's some work that only a few people see. And recently, we were writing a shareholder report. And a shareholder report, as it turns out these days, are rarely read. Rarely read. However, a few people read them. Our families read them. Okay? Our families read them. Our friends read them. Our employees read them. And so the team came to me and said, Jen-Hsun, look, this isn't something that hundreds of thousands of people are going to read anymore. That's the good old days. Now, only a few hundred people will read them at best. And so we've decided that we like not to, we don't need to put a lot of energy into it. Let's just make sure that it follows SEC's rules and reporting rules, and let's file it and move on. And I said, look, if one person reads it, we should put our heart and soul into it and do our best possible work. If one person reads it. And I mean that, and I believe that. Even if that one person is me. If I do something and I'm the only person that will see it, well, that would happen to be most of my work. Most of my work, most of your work, are work that you do and only you see, and only you judge. You are the judge. You decide. I happen to be one of those people that believe you still put your heart and soul into it. You do the best possible work you can, and you have no idea who will see it. You just have no idea who will see it. And if accidentally you were to see it yourself years later, you would like to be proud of that work. And so I think those two rules, which is doing important, relevant work, doing work that you're proud of, and over the long term, if you do that, you'll be surrounded by extraordinary people. You'll be surrounded by the world's best at what they do. And then almost anything is possible. And everything works out for itself. Okay, so that's kind of the, if I could summarize the NVIDIA story, and I've given you 30 years of rambling about our history. If you could take a little something away from that. We're in the process of reinventing ourselves again. 10 years ago, we came to the conclusion that the PC was going to continue to be very important, but in the future, mobile is very important and cloud's really important, and the way we compute is going to be radically different. And we asked ourselves, how can we put computer graphics into mobile, and how can we put computer graphics into the cloud? And as a result, we invented a bunch of new technologies. We're in the process of rolling some of that stuff out. If you get a chance, read about Tegra. Read about this new device that I just made called Shield, and read about this new system we just created called Grid. to put amazing computer graphics in the cloud. What we hope someday is that any computer graphics, as wonderful as they can be, is just one click away from almost any device. And when that's possible, we can expand the reach of computer graphics and expand the reach of video games, so that it's more convenient, it's more enjoyable, and we can open up the format and the medium even more. Okay. All right, guys. Thank you very much. Dude.
Okay, we can take a question or two here, and then we're going to move into 1001 for those who would like to be able to talk to Jen-Hsun. And so is there a question or two that you'd like to ask before we move?
I was kind of curious, like, when you do your startup, how do you fund that? And then how is that different today?
When you're a startup, how do you fund that, and how is that different today? We started our company, I guess officially, about this time 20 years ago, in the early part of the year. We didn't get funded until about June, and so between then, we were just living off of our savings, which in the case of Lori and me, we really didn't have very much savings. And so I don't think she ever said anything, but my recollection was that we were probably a month or two from had no money at all, but we had hope, we had hope on our side. The way that we got funded was good old fashioned Sand Hill Road. I went to Sand Hill Road. Somebody told me this is the way you started companies. I went back when I was resigning from my other job, LSI Logic, at the time. The CEO at that time was Wilf Corrigan. He was one of the most important. He is one of the most important pioneers of the semiconductor industry, and I did good work for LSI. And when I left, he didn't want me to leave, and I went to his office and I told him I'm going to go and build this 3D graphics company, and he goes, and at the time, the test of any smart idea is, okay, what's the killer app? Okay, because Lotus 123 was the killer app, right, of the PC. WordPerfect was the killer app of the PC. So what's your killer app? And I said games. And he goes, who plays games? I said, well, young people, we do. And he goes, give me an example of a game company. And I said, well, if we build the technology, then software companies could start. And he goes, you'll be back soon. And I'll hold your desk. I won't give it away. And then on the way out, he said, Don Valentine is the best venture capitalist in the world. And he was the venture capitalist behind Apple, the first round of Apple. Cisco, the only investor in Cisco. He invested in a company called Yahoo many years later, and Google many years later. And he was also the investor in LSI Logic. He goes, Don is the toughest VC in the world, and if you can convince him to give you money, you've got a good story. And so I'm going to call Don, and before I even left the office, he picks up the phone, he calls Don, and he says, saying, I'm going to send a kid down to you, and he wants to try to raise some money. Well, I didn't have the confidence to go right away, and eventually, and I bought a book and the book was written by a guy named Gordon Bell. Do you guys know Gordon Bell? You must know Gordon Bell. Gordon Bell is the father of the vax. Oh my gosh. Oh. What happened to the love of history? Someday somebody goes, who's Jen-Hsun? Whatever. Okay, so Gordon Bell, okay? So he had written a book how to start a company. And he was the father to VAX. He was the CTO of DEC, Digital Equipment, and then he started a company called Kubota to build supercomputers. He's now a chief researcher at Microsoft. Nice man. And so I met him earlier, and he wrote this book. I bought this book. It's the world's thickest book, and I never got through it. I came to the conclusion if by the time that I'm done with this book, I'll be out of business. And so I'm just gonna have to go. I gotta get my courage up and go. And so I went to Sand Hill Road. I looked up Don, and Don goes, okay, what's your story? What are you building? Who are you building for? Why are you gonna be successful? I had a hard time explaining what I was building, who I was building it for, and why I was gonna be successful. He goes, and on the way out, he goes, Wilf says to give you money. And against my best judgment, based on what you just told me, I'm going to give you money. But if you lose my money, I will kill you. Those were the last words that Don said to me, and he writes me whenever he reads about me in the paper. He always writes a little something. He says, Jen-Hsun, I'm really proud of you. He's one of the world's best venture capitalists. And he says this. He says, you should a killer product, a huge market, and a few good men. That's what he looks for. And I think the last part of it's the most important part. And the reason why it is because the original business plan that I never finished, and I couldn't have finished if I tried, because I didn't have the capability to really focus on the right things. At the time, but if I had finished it, it wouldn't have mattered, because he would have realized that business plan was gibberish anyways, and that the world is very complicated. The question isn't what is your business plan, the question is how do you reinvent yourself as the world changes around you so that you can continue to be relevant. And I think he was trying to say that in his very few words, and I've surely learned that over the years. But we raise money that way, good old-fashioned way, venture capital. Is there any other questions? Yes, sir.
Sorry, why isn't cloud graphics processing happened before now? Like, it seems like it's been possible for a while. Like, what's the bottleneck or whatever?
That's a really good question. We've been trying to work on it for 10 years now. Here, the fundamental problem is actually pretty complicated, and it's a speed of light problem. Computer graphics is interactive. We have about, which means that from the moment that you tell it to change to the moment that your eye sees it, if it's not within a few hundred milliseconds, and depending on your for people who play video games, if we don't change the graphics, in about 100 milliseconds you're going to see it. Okay, so from the moment that I touch the mouse or my controller, I've got about 100 milliseconds. Well, every frame time is already 30. Okay, and so I've got to get the signal into the system, through the operating system, into the microprocessor, into our GPU, process the frame, update the frame buffer, and send it to your eyes within about 100 milliseconds. Okay. Well, if it's in a cloud, that means your computer is not here. We've got to take the signal. We've got to take the control. We've got to send it over the WAN to a server somewhere. It's got to get through the connection broker. It's got to get processed on the server, and then now it's got to send that frame buffer back into your eyes. So at that point, we got to compress it, we got to stream it, and send it all back, and we got to do it all basically within about 100 milliseconds. If we do it within 200 milliseconds, I'm pretty sure most people won't notice. Avid gamers, professional gamers, will notice about somewhere between 60 to 90 milliseconds. When you're playing a video game on a PlayStation, because the TV has all these buffers inside for image processing, you could get it into what they call game mode, but most people don't know to do that. Most people are enjoying PlayStations at about 150 milliseconds. Okay, and you guys probably have you guys heard about Guitar Hero? Have you know that game? You know how when you get really good, you got to predict. What do you guys call that? There's actually a word. You guys have to predict the graphics that's about to show up. And the reason for that is because the latency of the guitar to affecting which one of the notes you're supposed to hit, that is too long for Guitar Hero. And so people have to guess. I mean, before you know it, the best gamers, the best ones, are actually predicting based on the music what notes are going to get hit. Okay, and so latency matters. In the case of cloud, it's too far away. And so the problem that we have to solve, number one, is latency, which translates to interactivity. The second problem is this: when you put something in a cloud, fundamentally, it's now shared by everybody. Right? When we enjoy Yelp, or you enjoy, whatever it is, Shazam, or whatever streaming, Pandora, whatever it is, you're sharing it with millions of other people. And so the problem with cloud graphics is, how do we take a GPU, which is really notoriously bad at context switching? Okay. A CPU is good at context switching. That's why it could support a lot of different users at the same time. But a GPU, our pipeline stage, from the moment that a command comes in to the moment that a pixel leaves into the frame buffer, is something along the lines of about 350 pipeline stages at 2 gigahertz. It's a long time. Unlike a CPU, it's about 20. And so our ability to context switch, our state is so full, we have so much state, that context switch from user to user is too difficult. It's taken us about 20 years to invent the world's first GPU, Kepler's the first one, that is virtualizable, that we can virtualize it, we can context switch it, we can share it among a whole lot of different users. And we can do it at a level that is so close to the iron that the operating system doesn't have to get involved. And so that's the second thing we have to do, by making it shareable. And the third thing you have to do is density. Now I've got to put 1 million GPUs in a server room to host video games for tens of millions of people around the world. And so that's the grid endeavor. That's the moonshot for us. How do we take something that is really designed for one person, a computer architecture that's really designed for one person, and make it shareable for a large number of people, and do it in a very cost-effective way? Because if you think about it, a PC with one of NVIDIA's GPUs in it is not your most affordable PC. It's probably a few $100s. Now we want to make it so that instead of a few $100s per person per year, we want to make it so that it's fractions of cents per person per minute. And so figuring out a way to increase the density, what they call concurrent users per node, is a technological challenge of pretty significant proportions. And so we've been inventing all of this stuff, and we finally put it all together, from the GPU to the system architecture to the hypervisor, the world's first GPU hypervisor, to the connection broker. We've put the whole thing together into essentially the world's first cloud graphics card, if you will. Okay, and it's called Grid, and hopefully we could start a trial here in the United States, this year sometime. So I'm pretty excited about that. But that's a big invention for us. It's the first of its kind in the world, and it also moves NVIDIA from being a chip company to a systems company. We're now building. Grid is basically a visual computing appliance, kind of like what a router is. It's a network appliance, and what a network attached storage is a storage appliance. Now you have a graphics appliance, and you take one of these appliances, you hook it on the network, and that's all she wrote. Yes, sir. I'll repeat your question.
You can talk about the top 3 things you got out of your OSU education for your company.
Yep. Top 3 things that I got out of the OSU education, and I didn't appreciate it at the time nearly as much as I do now. Okay. Number one, of course, is undoubtedly Lori. And at the time, I, gosh, she was lucky to have me. I'm just kidding, honey. But of course, but the people that you met, and in my circumstance, the person that I met, the people that I met was even more important than most. The thing I learned about there were a couple classes that I really made an impact on me at Oregon State, and it's one particular class was E.E. Fundy's, and E.E. Fundy's, the professor would Professor Amort. You guys, Professor Amort was fantastic. He always used round numbers, and I hated that. He would stand up on the board and he would solve these circuits, and in the textbooks you've got exponents, and when he's up in class he's just using round numbers. And in lab we're using SPICE simulators. In class he's ripping it out of whats, and they're round numbers, okay? And it used to drive me crazy. Instead of 0.68, he would just go 0.7. It used to drive me crazy. And I learned over the years that false accuracy is pointless, and that understanding first principles of the topic at matter, what are the most important variables, and what he was trying to teach us was what was important to focus on. Everything else was details. And it's good to know the details, but you can't lose the big picture. And he taught us that. To this day, I use round numbers on just about everything at our company. I can talk about just about any topic matter with round numbers. And now the employees call it CEO math. CEO math is surprisingly accurate. And the reason for that is because you never lose sight of the most important variables. And I thought that Amort was really fantastic in that. Probably the third thing I would say that was really important. I was always a good student, and academics was always really important to me. My parents only cared about one thing for the kids. We could do anything we wanted, just as long as we did our homework. So I was like, anything. It didn't matter what we talked to them about. The last thing they said was, okay, now go do your homework. So you just imagine, okay? Gee, Mom, I'm really hungry. Yeah, I'm working on dinner. Go do your homework, okay? Oh man, I just scraped my knees. It hurts like crazy. Okay, well, I think it's going to heal. Go do your homework. You could leave every conversation with go. It works really quite well, in fact, okay? Every conversation you can end with go do your homework. And so we were, academics was always a given for me. The thing that wasn't a given was living. Learning the social skills was quite new to me. I was young anyways, so when I was in McNary, I was the youngest kid there, and the young, a Chinese kid looks young anyways, but when you have a 16-year-old Chinese kid, with a basketball player on the same floor, it just doesn't look right. You know what I'm saying? It just doesn't look right. There's all these adults, and then there's this little kid, all the other kids were kind to me, and I found a new friend, Henry Weinhardt. They don't drink Henry Weinhardt anymore, huh? There's Henry Weinhardt, you guys, come on, the best Oregon beer. So I met Henry, and Henry and I were good friends. But it's living life, and to this day I would say that the social part of growing is as important as the academic part of growing. It's in my case, because I was so introverted and shy, it was very helpful to me. It would have been hard for me to. It's hard for me anyways to do this, but it would have been impossible otherwise. Okay.
Okay, thank you, Jen-Hsun.